Hello, everyone. Good morning or good afternoon, and welcome to today's webinar. Thank you for joining us today. My name is Mark Bignam, and I'm a senior cost modeler at aPriori. I'll be your host for today as we talk about driving innovation through additive manufacturing, and I have with me two fantastic presenters. First, my colleague, Dr. Amanda Bligh, who has 13 years of experience on how manufacturing cost evaluations early in design lead to innovative solutions. We're also excited to introduce you to Dr. Kirk Rogers from the Barnes Global Advisors, who brings deep knowledge in additive based on his 10+ years of experience focusing on the use of additive technologies to solve manufacturing repair and supply chain problems, both at GE and as an industry consultant. We have 60 minutes scheduled for today's session, and we will start with a discussion where Kirk will take us through the opportunities and advantages of using additive manufacturing, including reviewing the state of the art and considering how additive can support innovation within your business. Following that, Amanda will talk about how technology can assist in completing evaluations around additive manufacturing and drive toward early innovation. And she'll be talking about that in the context of a case study. All right, that's enough for me. Kirk, passing it over to you to talk about innovating with additive.
All right, thanks, Mark. So my company, the Barnes Global Advisors, is a small but mighty business that does a couple of main things. We work with companies such as yours on advising their additive strategy, finding and maturing additive manufacturing applications, performing due diligence, helping educate your employees using some training offerings, and then communications. We really like helping people build their story around additive and helping expose their company, both inside and their customers, to things that are innovative that they've done to increase brand awareness and link better with customers. And so our mission is to accelerate the adoption and industrialization of additive manufacturing across the manufacturing supply chain. We do that by being agnostic. So we work with all the different additive technologies, which we'll describe in a little bit, and we work across the supply chain, from powder producers to original equipment manufacturers of additive manufacturing and other machines, to engineering service providers, which we are as well, and to investors and inspection and post-processing, and really across the size spectrum, just as well as the AM experience spectrum. So sometimes it's a, hey, can I print this question? Sometimes it's a, hey, I've got this idea that my management won't support because I can't figure out how to get an additive business case to go. And this happens across companies from one person size that has just started in a garage to Fortune 100 OEMs, really, across aerospace, defense, oil and gas, academia, medical, energy, and automotive industries. So we've probably, anyone on this call has probably had a article about additive dropped on their desk, or found something in the local business magazine, or seen something in the news about this 3D printing, additive manufacturing technologies, right? And so there's been a lot of hype. And back in 2013 or so, when the light blue curve on this graph was generated, I would have told you that that hype was way overblown, that additive manufacturing as an industry wouldn't have grown that fast. But then look at the dark blue, right? That's an estimate 3 years later of the total additive manufacturing market, and it's significantly larger than the light blue prediction from 2013. Right now we're going through some unprecedented changes, and so 2020 might not be as rosy growth, but we expect that growth in this industry will continue, after maybe a 2020 pause. Maybe a 2021 pause. And so we're super excited because, not because the industry is growing, but because the applications are so varied and so broad. And so what can AM do? It can make things from very small to quite large. And so here we've just grabbed a few examples. The one on the very left is a miniature Eiffel Tower built by a polymerization process of polymers, and that total height of that exact scale replica of the Eiffel Tower is 1 millimeter. So can you imagine this large iconic structure being reduced to the size of 1 millimeter? The second one there is a Red Dot Award winner from 2017, which is an innovation award in the additive space. And Maria Sanchez designed and is modeling a dress printed on a typical 3D printer that you might find in your local library. The third example there is a more industrial example, topology optimized internal structure of an aircraft service door. Right, so by using next generation computing technology and traditional casting, this is a part that can be very, very much lighter and very, very much different looking than conventional parts. And in this case, is something like 30% lighter at equivalent strength of a conventionally manufactured door, and it takes much less time to manufacture. And the quite large example there is a printer company called Icon and a community development company called Mobile Loaves and Fishes, which is using 3D printers to print concrete homes for the homeless in Austin, Texas, and in some communities in South America. So, this is the breadth of what AM can do. And we love this breadth. And the reason why there's such a breadth is because additive manufacturing is really not just a technology, but it's a suite of tools that build parts layer by layer, usually starting from a platform. And so here are the 7 recognized categories defined by ASTM committee F42, right? And we'll go through them quickly from left to right. All right, so material extrusion there on the far left uses typically a filament or a pellet and is extruded through a hot nozzle and makes parts layer by layer by moving in X and Y and then incrementing in Z. So it's typically a hot process because we have to make the polymer hot enough to become liquid, right? And it requires some energy. And so those graphics, they're the red material graphics, the blue energy graphic, and then the density are kind of ways to think about these as different technologies and describe their inputs and outputs. So the second technology, binder jetting, is a powder bed technology that is interesting in that it basically takes a metal powder, spreads metal powder, and then uses an inkjet head, much like the inkjet head you might have in a printer at home, to bind the powders together into an object. And then after printing, you do a couple other steps, including a sintering step to get a solid metal object. Material jetting, the next one there, the third box, is a process that also uses inkjet-like jets, but instead of jetting just a binder, you actually jet the material that the part is made out of. And that material is then cured with either light and or heat in order to make a solid plastic object, right? Powder bed fusion, the middle box there is a technology that uses a laser or electron beam or other energy source to basically weld at very fast rates and very small weld pools to make solid 3D printed materials in one step. And this one can be used with both metal and with polymers. Directed energy deposition is typically a metal process characterized by putting either a wire or a powder through a nozzle, and the energy is also going through the nozzle. And so by spraying or extruding the input material through a hot nozzle and impinging it onto a base platform, you get a 3D printed part. The second last technology there, vat photopolymerization, is one of the oldest technologies. It's been available for more than 30 years. And essentially use a laser or another energy source to polymerize part inside of a vat. And in that vat of goo, right, then you extract the part out of the vat. Right? So it's been done kind of at the interface between the surface and the vat traditionally. However, there's some newer implementations of this technology that can make really interesting high performance polymers that traditionally could not have been done by these kind of photopolymerization processes. And the last process there, sheet lamination, is really one that I think everybody on the phone call has actually done, maybe in kindergarten. Right? So a sheet lamination, basically take a sheet, make it into a shape, or laminate it as a sheet, And what you did in kindergarten was, take red colored paper and blue colored paper and glue them together to make a face or a turkey or something. And sheet lamination as an industrial process uses different kinds of sticking, usually a welding kind of process, but can make very large objects quite cost effectively when done appropriately. And so this range of AM technologies is really what brings the ability to do such a wide range of interesting things in many different markets. Okay, so TBGA here stands for the Barnes Global Advisors, our company. And we think about additive manufacturing applications through a maturity model, right? So, the fancy thing that we saw, the aircraft service door is not something you could go and design and produce as a company tomorrow if you don't have any experience, right? So we typically think about your experience, our skills and knowledge gained by using a manufacturing process is in the maturity model here in the blue side, and the product requirements, what's required to make a product, is in the gray side. So at low levels of maturity, like level 0, right? So many companies have been using level 0 prototyping kind of technologies, made 3D printed objects for prototypes, for product development, and that's happened for many years, right? But the next step, a production influence. So using additive to either make, short run tooling or shop aids, right? You get your workforce gets to learn about the differences and how you have to think differently to use additive manufacturing to solve problems. One of the examples that a number of years ago, I bought a 3D printer for a manufacturing shop that I was working in at the time. And, within weeks, the maintenance guys were learning 3D CAD on their lunch break and in the evenings because they realized that printing jigs and fixtures and tools was much faster, and they could get, their fellow folks on the shop floor happy with the solutions that they create much more quickly than traditionally buying, a hunk of material and standing at a tool room lathe for half a day to make a fixture. So that has great variable cost productivity across most every enterprise. Right? Level 2 is the kind of question that most people ask of, hey, Kirk, can I print this part? And we'll give you an example of that later in the webinar. Right? So part for part substitution. Oftentimes this is great at the beginning or the end of, the product lifecycle for, new make kind of things, late design modifications, some testing artifacts and that sort of thing at the beginning of the life cycle of a product, but for spare parts at the end. Right, so instead of, if you declare end of life for a product and then you make 1 million more spare parts, you have to warehouse those spare parts. If you just save the design in a 3D printable format, then you can print parts as your customers need them as spares, for example. Level 3 is where, design really comes in, and you see interesting functional designs by unitizing parts. So that is taking multiple parts and smashing them together to make a better part that's 3D printable, but might not be makeable by traditional manufacturing. And then level 4, which is many of the examples that you might have had shoved on your desk by a manager or a vice president of, hey, how come we can't do this, that sort of thing, is really requires, world-class capabilities from a people perspective, and thinking about AM-enabled business models, features or subsystems that are engineered together to be made as one part and can meet all kinds of requirements, whether they're mechanical or physical or fluid flow or heat transfer, oftentimes better than the multi-part assembly that your company has traditionally made. And by making it one part, you often can eliminate a bunch of touch labor as well. So we think about the universe of AM solutions kind of in this maturity model. And next we'll give a couple examples, right? And so use case examples at level 1, right? So this is part for part, or as a production influence kind of level, right? Is things like the welding jig that's in the picture, right? End effectors for robots, soft jaws for your computer numerically controlled machine tools, right? Oftentimes inspection fixtures, instead of being a big heavy steel part, that only needs to hold a part in the right relationship so the CMM can inspect it, you can print a much more willowy structure that meets the needs and is then easier for the operator to move on and off of a CNC machine or on and off of an inspection tool. So there's lots and lots of examples at sort of the level 1 that can really bring cost productivity to a business, or can improve things like employee ergonomics. Level 2 example there in the middle is the bracket that is first flown on the commercial Airbus airplane. And you'll notice that bracket looks very much like a traditional multi-piece assembly or a casting. This bracket traditionally is in fact a casting, and Airbus investigated 3D printing really to help them understand the 3D printing supply chain and risks associated with that supply chain, as they were trying to, in later years, figure out ways to make parts that were much more lightweight and much, more interesting than this part, but they needed to have the security of supply. So the AM part looks very much like the traditional cast part. So in the they can get, an identical part, whether it's made by additive manufacturing or made by traditional routes, right? And so, a lot of times in level 2, we see spares and obsolete parts or printed functional equivalents. So another example that happens quite often in large assemblies is, your assembly can't be made because there's a part that's missing. A supplier can't deliver it. So if you can make a 3D printed surrogate, stick it in there, until the real one can be assembled, maybe that complex assembly can continue along the assembly line, as an example. The level 3 example here we've chosen for you is a heat exchanger. And so you see these sort of typical tubes welded to a plate that you see on small heat exchangers. And you compare that with the image on the left, which is a topology optimized, so made so to follow the heat versus the surface area that you can get with conventional methods. And in this case, that both heat exchangers fit in the same amount of space, but the AM one with the complex design on the right is 30% more efficient. So it can carry 30% more heat away than the traditional one and takes exactly the same space. So, simple example of level 3, but something that looks, very different, and might be a hard sell at some point. And so how do we encourage folks to, identify candidates for additive manufacturing? Right, there's a bunch of different ways. I've chosen to highlight 4 here. So, number 1 is complexity. So if you have a very, very complicated multi-piece geometry that's complex, that's hard to make, that requires multiple manufacturing steps in order to assemble, or has challenges in, stress, reliability, or thermal challenges because of the methods of assembly needed by conventional manufacturing, that's a good opportunity. So think of something as simple as a heat exchanger, right, that also needs to be a bracket. So instead of having a bracket and a heat exchanger, why can't that assembly do both? The bright red there in durability is really thinking about, where does a welded or a bolted joint fail in a product? Right? Is there a way you can optimize your product and eliminate bolt joints, brazed joints, welded joints, right? Or does the machine tool, limit the that you're using, limit the geometry? So durability is often a good thing, looking at, part failures and assembly failures and why, and could you re-engineer that for better life using additive manufacturing and maybe putting 2 or 3 parts together as one. Time is another great way to think about it. So think of a complex assembly of something that takes a lot of touch labor or has multiple manufacturing steps. Can you reduce manufacturing steps by making a multi-piece assembly one piece? And maybe the time pays for it instead of the actual part cost. And the other thing is the limitation in identifying candidates is size. So actually I was on the phone yesterday with a company who wants to make a quite large arc segment, and they were having problems finding someone who could make it, for example. That being said, the equipment is continuously increasing in size. So, a few years ago, say 2015, 2014 timeframe, the biggest traditional machines on the market for laser powder bed fusion were 250 millimeters square bed. So anything more than about 10 inches by 10 inches wasn't buildable. Today, those are 400 millimeters to 1,000 millimeters in size. And so making something that's 30 inches or 40 inches is quite possible today. Right. If we look at the economics of additive manufacturing, just in a quick way with a trade study we did a number of years ago. So if you think about the legacy method, which is illustrated in red here, right, taking a block of material and carving that block using subtractive manufacturing and machining into 3 brackets. Right? We take relatively low cost material, although this is titanium, so it's not that low cost. Right? We spend a lot of time, effort, and money machining 25 pounds of material, or kilograms, excuse me, of material away from the block that we start of in order to deliver a part to a customer at a cost of about $3,500. If we look on the right side, and as illustrated in gray, if instead building those 3 brackets up from a base plate, right, we end up using considerably more expensive material. In this case, it's still titanium, but titanium powder is expensive. Right? Printing at a relatively common sort of rate, doing some machining. So instead of doing lots of volume machining, we only do surface machining to get to the same net shape for a total part cost of about $1,500, which seems a lot more attractive to me. Right? And so, total cost savings on those 3 brackets is almost $2,000, which is nothing to sneeze at for this titanium. Okay, so if we look at overall additive manufacturing markets, right, aerospace sort of led the way, and medical. So medical, aerospace has been flying military jets with additive printed parts for more than 20 years. Commercial jets have been flying plastic 3D printed parts for a number of years, and really getting some great innovation in printed metal parts because of the demands of lightweight, strong, durable, but high complexity that aerospace brings to each individual part. On the medical side, knee and hip implants sort of led the way, followed by spinal implants, and dental sort of reconstruction has been used for a number of years. On the knee and the hip side, the first commercially implanted knee and hip implants both surpassed 10 years in their respective patients last year. Luxury goods has been an interesting adventure in that being able to customize a ring or a necklace using additive is quite effective. And so lots of luxury goods, you may not even know you've bought something that was 3D printed because the luxury good company wouldn't let you know that. But it may have been instead of a more traditional cast process, which is how most jewelry is made. Automotive is really kind of in the nascent side. So bespoke autos like Bugattis and other high-end, low-volume automobiles use very few, but use significant printed parts. For some of those high-end cars, if you wanted to customize the interior and get your name put into the dashboard or into the shift lever, it's quite possible, and they do that by 3D printing. More and more, we see traditional automotive companies using 3D printing techniques to lightweight their vehicles or lightweight components, and that is often coming from the racing industry and kind of pushing back down to normal sort of automotive. In the energy industry, the demands of deep hole drilling and sour gas have driven conventional manufacturing to adopt additive, as well as the high cost of failure and the need for rapid response in times of like an oil spill. And designing and engineering custom solutions to problems in the energy industry has also led to some interesting advances using additive manufacturing. And for defense and space, there are numerous applications, lots of satellites in space with 3D printed components on them, lots of rockets of the reusable type that you've seen from SpaceX and others that also feature 3D printed components because it's the most cost-effective way to make low volume, high complexity parts. And with that, I'll turn it over to Amanda.
Great, thanks, Kirk. Now, I'm really excited to talk to everybody today about the case study that Kirk and I had worked on. But first off, let me introduce you a little bit to what we do at aPriori. So at aPriori, we help a number of roles throughout the manufacturing organization. And we do that in a number of different ways. First off, it's to help make decisions faster by estimating cycle times and costs based off of your digital twins and CAD files within our factory models. We also help you to work faster by automating the feedback of manufacturing insights and providing that to engineers, as well as automating some processes within sourcing. We also help you to work smarter by using the data that you already have within your systems to drive our models, as well as putting our own inputs where you need them, maybe in your PLM system, ERP, or in your other systems. And with our new cloud capability, we allow this to happen anywhere, and which is even more critical now to help support collaboration across your organization. So let's take a closer look at how we actually support these efforts within our product. With our software, we can read most major 3D CAD systems and analyze them. And as we do the analysis, what we do is evaluate the design geometry, the material type, and the production volume in order to estimate a cycle time and cost. Within the space of additive manufacturing, we support a number of different processes that Kirk had mentioned earlier. So SLA, polymer and metal powder bed fusion, and material jetting. As we do these types of evaluations, we can see an example in the upper right-hand corner of additive manufacturing. We determine a build direction, we determine what support structures may be needed based off of the type of process that's selected. And we also nest the part onto the build plate. And by doing so, as I mentioned, we end up capturing that printing time, but we also figure out what secondary operations are required based off of the printing process that we're using and the requirements of the part. So this can include things like break off of those support structures, secondary machining of surfaces, cleaning to remove dust and other materials that accumulate during the printing process, as well as secondary heat treatment and sintering. And again, we are getting driven on that based off of the support structures that we're calculating, as well as the tolerance information that we're pulling from the part itself. Before we move on and start taking a closer look at the case study, I think it's time for our second poll, where we're going to focus on understanding how you're evaluating if additive manufacturing is currently appropriate for your parts. It looks like we see a lot of people who are using quotes in consultation with suppliers, some with internal expertise, and some use of previous data, and then we have a reasonable number who are also doing no evaluations currently. So hopefully by what we show with our case study, you can gain some understanding about how, with aPriori, we can support making these types of assessments and trade-offs. Here we have our case study, which is a part from the aviation industry, which is a valve actuator housing. And this is a part that Kirk and his team use within some of their training. So Kirk, would you like to tell us a little bit about it?
Sure. So this is a part that I was asked to do a level 2 part-for-part replacement on when working with a large company in the aircraft engines business. So traditionally, this part is made with die casting and is made with a high permittivity material that's like 50% iron and 50% nickel. What we did as a quick case study a number of years ago was see that we could redesign it just a little bit and use laser powder bed fusion to print the part out of stainless steel, which had the magnetic properties required. And that took us about a week or two in order to do the evaluation and say, yes, we could print this part and we could do a low volume sort of run of maybe 100 parts of it.
Great, thanks for that introduction, Kirk. So what we're going to do with the case study here today is to assess quickly if this is an economical part for additive manufacturing, and if yes, under what conditions. And so what we'll do is we'll compare additive manufacturing to some standard processes. So die casting, as Kirk mentioned, which was the initial intent for this part, as well as investment casting. And one thing that we'll be able to do is to include some additional considerations. In the economic evaluation that Kirk showed earlier, he was focusing primarily on the material cost and then some of the processing cost. Within the context of aPriori, we're able to assess this a bit more based off of the impact of setup and how a batch size will drive that, as well as the amortization of the tooling that's required for some of our other processes. So within aPriori, we make investigations really easy. And so when I ran through this investigation myself, my first step was to load the CAD file into our system. And then I was able to very quickly create the 3 different options, one for investment casting, one for die casting, and then one for additive manufacturing, where I used metal powder bed fusion. Based off of those first 3 options, I could use one of our newer features called matrix costing to very quickly create a selection of different scenarios with various annual volumes and various batch sizes to start to understand where breakpoints might be. After I completed those, I was able to generate the reports. Now, as Kirk mentioned earlier, and I'm sure since many of you work with your suppliers to do these evaluations currently, you know that this can take days or weeks in order to get even these first options back. But doing a large selection of different values based off of annual volumes, based off of batch sizes, can take even more time. I was able to do this analysis in less than 2 hours in order to get all of this information out. We can see definitely a time advantage there. Now let's take a closer look at how the costs break down and what we're able to see within the context of aPriori. First off, what we want to focus on is what's known as fully burdened cost. And fully burdened cost includes not only the more traditional things we think of when it comes to a part cost, such as the material cost and processing cost related to labor and the machine time, but we also include the capital costs. So these are the one-time costs related to maybe the hard tooling that we see for investment casting, so around $10,000, die casting around $20,000, and then with additive manufacturing, we have one-time costs related to programming and fixturing that come in at about $600. Now we take and split that over the total number of parts that we're making in our run. So in this case, it's 1,000 parts over 5 years, so 5,000 parts. And that gives us an amortized value that we assess to each individual part. In addition, another thing that's driven based off of how we select our batch size is an amortized batch setup. So when we select a batch size, we split the amount of time it takes to set the machine up and the cost related to that across the parts in the batch. And so we can see that here. And so what we notice is that we see that die casting in this type of scenario ends up being the least cost because though the investments are low for both investment casting and additive, as well as the batch setup, some of the other costs are much higher, such as the actual cycle time, which will drive the labor and overhead costs much higher for the other processes. But it's important to understand this is just a snapshot. This gives us one example, in this case of 1,000 parts with 12 batches per year. But what we want to understand is where those breakpoints are, so we can make the best assessment possible and the best choice for our individual part. So here we can start to see the trade-off points between these different processes. We're running at 1 batch per year, so this might be a case where you have very low or no inventory cost, or you're taking and you're turning your parts directly into your product. So you're not taking any time out where they'll be sitting around. And so we have 2 trade-off points that we can highlight here. The first is between investment and die casting at around 40 parts, where we can see that the investment casting initially starts off a bit cheaper, due to the fact that the tooling cost is much lower for investment casting than die casting. But once we get to the around 40 parts, that breakpoint is hit where those other costs start driving the cost of the investment casting part, and die casting becomes much cheaper. We see a similar type of behavior around 100 parts for additive manufacturing. And when we're making less than 100 parts, we can see that additive is much more cost effective than die casting. But once we hit that point, we split over to die casting being more cost effective. Now, let's take a look at changing that number of batches per year from 1 to 12. And when we do that, we can see a shift of where these behaviors happen. So first off, we have probably at about 10 parts, we start to see the shift from die casting, from investment casting to die casting being more cost effective. And then the shift moves slightly as well for additive manufacturing, where it is more cost effective, but at about 65 parts or less when we're running more batches per year. So where does this leave us? Now, our goal was to see, is this an economical part for additive manufacturing? And yes, it is, but we do have some things to take into consideration. And so that is the number of batches per year, as well as the annual volume. And so as we're working our way through the product development process and we're determining, is this part a good fit for additive? The first thing we'll want to do is to confirm how many parts do we anticipate making per year? How many years are we going to make this part? And then what's our production rate? What are the number of batches per year that we're going to require? And then based off of that, we can run these iterations to start to see, is additive feasible from an economic perspective? And where are those breakpoints as to when it is? Because as Kirk mentioned earlier, the original case was to see, does this part make sense for a limited volume run within additive? And in this case, it may. And so in that case, what we may want to do is exactly what Kirk's team did, is to redesign this part so it's even a better fit for additive within the terms of that specific run. And from there, you would work on to continue your design process. So I'm going to hand it back over to Kirk for a second so he can give a little bit more context around how this type of investigation can help drive innovation further within additive manufacturing.
Thanks, Amanda. So, looking at the case study you just saw, and it's pretty obvious that, a tool like aPriori would be a great way to quickly identify lots of opportunities, even without doing some redesign for additive, right? And also potentially evaluating, what happens if I redesign for additive, even if it's just a conceptual design, that throwing it back through a quick analysis that only takes, a few minutes is much, much more cost effective than trying it, printing it, evaluating the results, and going through the actual physical analysis cycle. The second area where we really think these kind of tools can help is to evaluate use cases, right? So if you don't really know what the business case is, but you think it might work, you do the virtual simulation using the tool, and you can say quickly, oh, my fixture, if I do it this way, is going to cost half and it'd be twice as fast as if I did it traditionally with Joe's tool shop down the street, right? You can balance lead time. So oftentimes in the design and production cycle, maybe you could take a little bit more cost and use additive for the first 100, 200, 300 parts, and then switch over to a more cost-effective high volume production situation, right? You can also evaluate the idea of part consolidation, right? Just quickly joining CAD in 2 or 3 or 4 parts and then redoing the analysis in a tool like aPriori would give you a good indication of whether that complexity can be well supported by additive and what the cost implications might be. And again, and like we talked about before, evaluating the cost of storing many spares or producing low volume of end of life parts for something that maybe has been out of production for a long time, and it's difficult to get spare parts because the original manufacturer of those parts is out of business, for example, right? And the other thing is really highlighting insights for improvements. So again, using a tool like aPriori to take your preliminary design for additive and give it a cost. So hey, this moves the needle so much. I need to go back to redesign, right? Where's the limit? Where's the practical lowest cost point, for production by the chosen method, and also to quickly evaluate something that's been redesigned with a generative or a topology optimized tool, right? That you get output from that tool and you can feed it into a tool like aPriori in order to assign a cost for something that looks otherworldly that even the best manufacturing engineer in your company probably couldn't assign a reasonable cost to, because it's just so different.
All right, thank you so much, Kirk and Amanda, for the great content. We're going to move into the question and answer portion of this webinar, where we'll answer as many of the questions that were posted as we can. So on to the questions. Kirk, I think this first one is probably for you, which is, which additive manufacturing technology has the biggest market share and why? Not sure if you have that data on hand, but would be interested to hear your insight.
Yeah, so traditionally, it's hard to say because the use cases are so different. What we see a lot is many material extrusion, FDM kind of polymer machines all over the manufacturing enterprise. So from a polymer perspective, that material extrusion is probably the number one. On the metal side, the AM adoption has really been driven by medical and aerospace. And so you see laser powder bed fusion is probably the dominant technology there. And that can be done with both plastics and with metals. And so those technologies have been around for more than a decade and are quite well instituted both in the supply chain from an OEM perspective, as well as there being more than 100 service bureaus that you can throw your part to, and they can give you a cost and lead time for a product.
Great, thanks for the insight, Kirk. All right, I think this is another one probably for you, Kirk, and it is, when we're evaluating additive manufacturing as an alternative, what are the primary areas of difficulty, and how do you see that improving over time?
Oftentimes, the primary area of difficulty is building a business case, because the economics of production are so different, and most companies don't have experience. The kind of second big area is internal team knowledge, finding an expert to help either redesign a part or an assembly. And the third area is then finding and evaluating either a production partner or the right technology to do that part or assembly on. So those are kind of the big hurdles that we see.
Great, thanks. And this is kind of related to that as well. The question on how differently are parts designed for additive versus those designed for conventional processes?
Absolutely, completely different. So for conventional processes, right, the lowest cost part is the simplest. So take a block, remove what you don't need, you get optimized part. By additive, take nothing, add only what you need, and then you have the lowest cost part. Right, so the mental shift is actually a huge barrier for most people to adopt. And so, the tools that are helping are things like, Autodesk Fusion 360, where you can do a design and then quickly topology optimize your requirements for that design and get something completely different. Or online tools like Paramatters that can, optimize design for mechanicals, thermals, and vibration all at the same time. You define what you need from an interfaces perspective and what the loads are and the use cases are, and in minutes, right, you get a cloud-based solution that will be relatively easy to 3D print, but would be very difficult to do conventionally. And so, the designer's mindset must be very different for good, successful additive than with traditional manufacturing in general.
Thanks, Kirk, and set us up well for a couple questions that I think are more for Amanda. First, there's, as Kirk mentioned, some of these generative design tools, there's a lot of interest in innovating with additive, using those generative design tools. Can aPriori evaluate parts produced with those generative design tools?
aPriori works from a 3D CAD file, and so if it's possible to move a part from a generative design result into a 3D CAD, then we are able to do that. Kirk mentioned Fusion 360 and their generative design. We currently have a partnership with Autodesk, and aPriori is very well suited to evaluating parts that come out of Autodesk's Fusion 360 generative tool in particular.
Great, thanks, Amanda. And one more aPriori specific question is, what other processes are relevant for trade-off in aPriori with additive manufacturing? I know you had an example with investment casting and die casting, but are there others?
Right, and so we also support sand casting and machining type processes. So the example that Kirk had shown earlier with the brackets, where he did the material and processing trade-off from the standpoint of milling something, that is a trade-off that we can support within additive manufacturing, against additive manufacturing as well. Now, those are the metal processes. There may also be a case where you have some sheet metal, which aPriori supports the evaluation of as well, and against an additive counterpart. We also support a number of polymer processes, including injection molding and sheet plastic. So in the case of some injection molding in particular would be a good match for a lot of the polymer processes as an opportunity to do a trade-off.
Great, thanks, Amanda. Next question might be for either of you. I'm not quite sure who would be better to answer, but question is, additive manufacturing material properties have been a main limitation to adoption in some industries. Has there been any advancement in that domain, and how do current additive materials perform relative to other forms of engineered materials like castings or forgings?
Hey, thanks, Mark. I think I could take that. Yes, there's been quite a lot of motion in qualifying and certifying flying hardware. Several aerospace companies have released data sets for toughness, strength, fatigue for the materials that they're interested in order to grow the supply chain. And every week there's a new either ASTM, ISO, or SAE AMS standard released, it seems, that has some base design properties for an additively manufactured material. In general, if you think about a well-run additive process, the material performance tends to run in between a casting and a wrought product or a forging. And so the properties may be a little bit lower than a wrought product or forging, but is nearly always improved over casting properties.
Thanks, Kirk. I think we have time for maybe one or two more questions. This question goes to serviceability design. The question is, design engineers often will select fasteners to assemble various parts together with the intent of making that assembly more serviceable. How does 3D printing that design address the issue of being able to service assemblies?
In general, design the same way for that sort of serviceability. But imagine if instead of 3 or 4 fasteners, you could make a interlocking design with only one fastener. Could even be more serviceable than a conventional design. Right, with that geometric freedom, you can really open up a world of possibilities and a whole new way to design. Exactly. Right. So you think about, what many, we have in our house, in our office, 2 versions of a Herman Miller chair that's been in production for 30 years. The one I have is 15 years old. It is not designed for disassembly. It's not designed for recycling. The one my wife has, which is only 2 years old, I can take apart with one Allen wrench and do individual components of metals and plastics. Right. So the serviceability of the new chair far surpasses the serviceability of the old chair.
Very cool. Very interesting example. All right, I think we got time for one more quick question. That is around custom additive parts in aPriori. And person's wondering, parts can be built in different directions with additive. How will that impact the cost, and can aPriori help to quantify the impact of using different build directions to manufacture a part?
Yes, so within the context of aPriori, we have the ability to evaluate different build directions within the software, and it does influence the cost. Normally, the guidance is to reduce your Z direction in most cases within the context of additive to reduce time. And so within aPriori, you have the option. We choose a build direction based off of heuristics that we use in order to help reduce the time and based off of best practices within the additive space. But we also consider the situations where you may want to slightly change the build direction. And so we do offer the ability for you to override that and choose a build direction that may be more appropriate.
Thanks, Amanda. Thank you all for attending, and thank you for your attention. And thank you to Kirk and Amanda for the great presentation today. Again, thank you for joining, and hope to talk to you all soon.